Prep 2. Today we'll continue our course. Unit 1, Lesson 2, Wave Motion. As we studied before, that we are going to study two types of periodic motion. Motion that is repeated at equal periods of time. The first one was oscillatory motion, and the second one is wave motion. First, what's meant by wave, and then what's meant by wave motion. Wave, for example, I have a tuning fork. When we hit the tuning fork, the flame of the candle will move right and left, but it won't be turned off. Okay? So when we make a sound, the particles of the medium will vibrate side by side. Every particle will push other one side by side without leaving their positions. So wave motion depends on vibration of the particles mainly. So what's meant by wave? Wave is a disturbance, the disturbance that occurred due to hitting the tuning fork. It's a disturbance that propagates, the disturbance propagates without transferring the particles. Just the vibration propagates and transfers energy. According to what energy? Okay? In the direction of propagation. Examples on wave motion. When you push a piece of domino, each one will push the other without leaving its position. So the disturbance resulted from pushing any one of them. The disturbance, the change, will be transferred without transferring the pieces from their places. Okay? In case of water waves, when we throw a stone in a tub containing water, water will form something like waves without leaving the container. Okay, so it's a wave motion, depends on the vibration of the particles. So wave motion, the motion produced as a result of vibration of particles of medium at a certain moment when we make a disturbance, like hitting anything, talking, okay, and in a certain direction. When we push a piece of domino like this, it will move in the same direction, it won't move back. Okay, so wave motion, the motion produced as a result of vibration of the particles of the medium at a certain moment and in certain or specific direction. What's meant by the line of wave propagation? The line through which the wave will move. For example, source of the wave and the target. The wave will move from the source to the target, okay, through a line which is called line of wave propagation. Like this. This line is called line of wave propagation, the line through which the wave will propagate or transfer. Okay? The line through which wave propagates. To classify the waves like light waves, sound waves, water waves, microwaves, radio waves, to classify them and to divide them into types, we have to know according to what? According to what are we going to classify the waves? Number one, according to the direction of vibration of the particles. For example, some waves will cause vibration like this, up and down. Another waves will cause vibration for the same particles like this, side by side. Or according to the ability to propagate and to transfer from place to place. According to the direction of vibration of the particles, they are classified into transverse waves and longitudinal waves. According to the ability to propagate and transfer energy, they are classified into mechanical waves and electromagnetic waves. We will study them in details right now. Number one, according to the direction of vibration of the particles, how the particles vibrate to transfer the wave from place to place. First, transverse wave, and second, longitudinal wave. In transverse wave, the particles will vibrate perpendicular to the line. For example, if my arm is the line and the wave will move from this place to this place. This line resembles the particles of the medium. When I make the wave and this wave is a transverse wave, particles will vibrate like this, up and down, perpendicular to the line. Okay? Like these waves, they move up and down. Particles will move up and down, perpendicular. Like the light waves, radio waves, and water waves. Okay? While in case of longitudinal, waves in which the particles of medium vibrate along, they move in the same direction of the line, side by side. They push each other. Okay? Like this. They will be collected in an area and rarefy in another area, and collected and rarefy, etc. Compacted and less compacted, compacted and less compacted, without moving up and down, just along the line. For example, sound waves. So when I ask you, sound waves are longitudinal waves. They are not transverse. Light waves are transverse waves. Give reason: because the particles vibrate up and down, because the particles vibrate along. The other way, we will continue transverse wave and longitudinal according to the composition of each wave. For example, transverse wave has two main points, which are crest and trough. Crest at the top, trough at the bottom. Crest means the highest point of particles. The highest point reached by the particles is called crest in transverse wave, while trough means the lowest point of particles in transverse wave. In case of longitudinal, we have places, not only point up, point down, crest and trough. In case of longitudinal, we have two places or two regions, which are compression and rarefaction. Compression and rarefaction. Compression contains many particles, compacted, pressed, high density, while rarefaction contains low amount of particles, rarefied. Okay, and rarefied means it looks like empty, but it's not empty. Okay, low amount of particles. Area in longitudinal wave that has high pressure, high density, compression. Low pressure, low density, rarefaction. Longitudinal waves consist of space and space, compression and rarefaction. Transverse waves consist of space and space, crest and trough, highest point and lowest point. According to the ability to propagate, the other wave classifying, we classified them before according to the direction of vibration. Now we will classify them according to the ability to propagate and transfer energy from place to place. They are classified into mechanical waves and electromagnetic waves. Mechanical and electromagnetic. According to what? According to the ability to propagate. They are classified into mechanical and electromagnetic. Mechanical waves, they need a medium and they can't propagate through space. There must be solid or liquid or gas to transfer them. There must be a solid or liquid or gas to transfer them. Okay? Maybe transverse or longitudinal. For example, sound is mechanical, but it's also longitudinal. And they have low velocity. They are slower than electromagnetic. So mechanical waves, they need a medium, solid or liquid or gas, to transfer from place to place. While electromagnetic waves, they can propagate through vacuum or space. And they don't need a medium, and they have very high velocity, which equals 3 times 10 to the power 8 meter per second. A very important value. 3 times 10 to the power 8 meter per second, the velocity of electromagnetic waves in the space. Okay? Examples, sound waves and water waves, they need a medium to transfer from place to place, and that's why we can't hear solar explosions, because sound can't transfer from the sun to the earth, because there is no medium to transfer sound from sun to earth. While in case of electromagnetic waves, we have light waves, microwaves, radio waves. They can move through medium and through space as well. They don't need a medium. Concepts of wave motion. As we studied before in oscillatory motion, we have 4 concepts, which are amplitude, complete oscillation, periodic time, and frequency. In case of wave motion, we have 4 concepts. Wavelength, a new concept. Amplitude, an old one. Frequency, an old one. And the wave velocity, a new one. We have 4 concepts. The first one is wave amplitude. What's meant by amplitude? The maximum displacement. But in case of oscillatory motion, we say the maximum displacement made by oscillating body. In case of wave motion, we don't have oscillating body, we have particles. So it's the maximum displacement made by particles of the medium away from rest positions. Again, what's meant by amplitude? The maximum displacement made by particles of the medium away from rest position, and it equals 6, the maximum displacement. Wavelength. What's meant by wavelength? It differs from transverse to longitudinal. According to what? According to the composition. For example, wavelength of transverse wave means the distance between two successive crests or two successive troughs. Like this one, between crest and crest, it's called wavelength. Between trough and trough, it's called wavelength. Length of only one wave. In case of this one, between crest and crest, it's called wavelength. Wavelength of what? Of the transverse wave, because it has crest and trough. In case of longitudinal wave, it's called the distance between centers of two successive compressions or rarefactions. From the center of compression to the center of the next compression, or from the center of rarefaction to the center of the next rarefaction. In this case, I want to measure the wavelength, the length of only one wave. From this crest to this crest, 8 meters. 8 meters has many waves. To measure the wavelengths, we have to divide the distance covered by waves, 8 meters, over the number of waves. Again, the distance covered, which is 8, over their number. Wavelengths equal distance, which is 8 over 4. 1, 2, 3, 4, 1. 1, 2, 3, 4, 2. 1, 2, 3, 4, 3. 1, 2, 3, 4. 4 complete waves, not oscillations. We are talking about wave motion. I have 4 complete waves taking 8 meters. So each one takes 2 meters. It's called wavelength. Again, distance over the number of the waves. In a problem like this, calculate the wavelength, same rule, of wave if the distance between the second crest to the 7th crest is 20 meters. I have the distance, but I don't have the number of waves. He told me from the second crest to the 7th crest. From the second to the 7th, 7 minus 2, 5 waves. Okay? Wavelength equals the distance covered by wave over number of waves. It's okay. Wavelength equal 20 meters and 5. I have 5 waves. Why? Because he said from the second crest to the 7th crest. From the second to the 7th, there are 5 waves. For example, from the 3rd compression to the 5th compression, 2 waves only. From the 3rd to the 5th. Okay? Frequency, what's meant by frequency? The number of waves made in 1 second. Same rule, frequency equals the number of waves over the time taken. Same old rule. But instead of saying the number of complete oscillations, we will say the number of waves over the time. The law of wave propagation, the last part. There is a law to measure the speed of the wave, which states that the velocity equals the frequency times wavelength. Velocity has a measuring unit, meter per second. Frequency is hertz. Wavelength is meters. In a problem like this, if the frequency of the wave is 200 hertz, the frequency is 200, and the wavelength is 5 meters. Calculate the wave velocity times. Wave velocity equal frequency times wavelength. 200 times 5, 1000. 1000 what? Meter per second. The measuring unit of velocity. Meter per second. Another problem, if the frequency of the wave is 200 hertz and the wave velocity is 400 meters per second, calculate the wavelength. Okay, to measure the wavelength, we have to make velocity divided by frequency. Wavelength equal velocity over frequency. 400 over 200 equals 2 meters only, not meter per second, because I'm measuring wavelength, which is measured in meters. Law of wave propagation, velocity equal frequency times wavelength. The relation between velocity and the frequency, for example, when the frequency increases, velocity will increase. And when the wavelength increases, velocity will increase. while when the frequency increases, wavelength will decrease. So the relation between velocity and the frequency is direct. Between the velocity and the wavelength is direct as well, because when the wavelength increases, velocity will increase. While the relation between frequency and wavelength is inverse, as we say. And thank you for watching. I hope you understood it. Thank you.